In this example, I'm going to consider a bar with mass on some pivot point. And I'm going to think about the torque as measured from the 0 centimeter mark here at the end, the 50 centimeter mark here in the middle, and the 100 centimeter mark here at the other end. This bar has forces on it due to gravity from its own mass and due to two masses attached, one at the 10 centimeter mark and one at the 70 centimeter mark. A trick for solving this problem that you need to know is that gravity tends to act on the middle of things. Or rather, if we were to sum up the interactions of gravity at every point, we would see that it's equivalent to talking about the gravity acting on the center of something, whichever way you want to think about it. First, I know that each of these masses has some force associated with it due to Earth's gravitational field. So I'm going to go ahead and find the forces at these places. Here on the bar, because of the 112 gram mass, there's going to be a force due to gravity. And I find that with force due to gravity equals mass of the objects times the strength of Earth's gravitational field at the surface of the Earth. And I'm going to, for simplicity, call G 10 meters per second squared, or even better yet, 10 newtons per kilogram. So for every kilogram of mass, gravity is going to apply a 10 Newton force. Now this is instead of doing 9.8 meters per second squared, because I can just look at the numbers and quickly multiply by 10. So starting here, 112 grams is 0.112 kilograms, so this would be 1.12 newtons. 224 grams is 0.224 kilograms, and this would be 2.24 newtons. So to multiply by 10, all I'm doing is moving that decimal over one place. The 50 gram bar would be 0.5 newtons, and that's gravity down. This is gravity down. When we talk about torque, it generally makes sense to consider torque clockwise and torque counterclockwise. So you have to think about a clock, and clocks tend to tick this way. So this is clockwise, this is counterclockwise, opposite the way the clock goes. Torque clockwise, and we're going to first consider the 0 centimeter mark. This is just the sum of the forces that cause the bar to want to rotate clockwise. Just going to notate that with my drawing. So the things that would make the bar about this pivot point want to spin this way, clockwise. And since we're summing, I need some summation index times the radius. So that's how far they are from the pivot point. If you just think about the torque equation, force times radius. So if I'm doing a bunch of them, I'm going to sum up all the forces and the radii. So in the example, that probably makes a little more sense if I just write it out. So let's start doing this. The torque clockwise will be caused by this force. It's pulling down, and if we're thinking about a rotation axis here at 0, it'll make the bar want to spin this way. So that force is 1.12 newtons, and the standard unit for torque is Newton meters. So I want to go ahead and convert 10 centimeters to meters, 0.1 meters, plus the weight of the bar will also make it want to spin this way. That will be 0.5 newtons, 0.5 meters, 50 centimeters. And finally, this mass over here will make the bar want to spin this way. So that's 2.24 newtons times 0.7 meters. I'm going to save torque counterclockwise for a second because I want to be explicit about all my steps, so let's just keep doing this. If I multiply each of these, here in the first term I get 0.112 Newton meters plus 0.25 Newton meters plus 1.57 Newton meters for a net clockwise torque of 1.9 Newton meters. Then if I want to do the counterclockwise torque, first off, if this were an equilibrium problem, so if you knew for sure that this bar were not spinning, then the two torques would have to equal each other. Just like if we're not accelerating, we have a net force of 0. If we are not having angular acceleration, then we have a net torque of 0. The only thing that might make this bar want to spin counterclockwise is the normal force from this point here. So think about it. If the bar isn't falling, then this pivot point has to be supporting it. And it has to support all of the weights of these things in order to make sure we don't have a net force. Because if we have a net force other than 0, this thing will either fly up or fly down. So I've already found each of those weights, and if I just sum them up, so 1.12 plus 0.5 plus 2.24, I find that the normal force up to hold up all of these weights must be 3.86 newtons. So that means for my counterclockwise torque, I have 3.86 newtons as my force, and remember gravity tends to act on the center of things. Actually, that's a bad thought here. It's not gravity that's pushing this thing up, it's the pivot point, isn't it? So the normal force from the pivot point is applied right where the pivot point is, and that is at the center of this bar. So I have my radius of 50 centimeters, which would be 0.5 meters. And if I multiply that out, I once again get about 1.9 Newton meters. Now, let's think about the halfway mark, so 50 centimeters. And now that you've seen the pattern, I'll go a little bit faster. So, if we're considering the 50 centimeter mark, each of these forces, the one pointing up here, the normal force, and gravity pulling down, are right at 50 centimeters, which means they have a radius of 0. And anything times 0 is 0. So if I'm considering forces that will make the bar rotate around this point, everything at this point gets thrown out. Forces at the pivot point don't affect the rotation. And that's an important point when dealing with torque, because we can often just throw out some forces if we're smart about picking where our pivot point is. Now, the problem has specified my pivot point, but because I have two forces right at the pivot point, I can safely ignore them. And again, that's just because my radius is 0 for those, and anything times 0 is itself going to equal 0. All right, if we're considering the pivot point here, so if I hold the bar here and put these two weights, the weight over here on the right will make it want to rotate clockwise, and the weight over here on the left will make it want to rotate counterclockwise. So this will be causing a clockwise torque, this will be causing a counterclockwise torque, and we're ignoring the two forces right at the pivot point. So for torque clockwise, all I have to do is this weight, 2.24 newtons, times its distance from the pivot point. So measured from 0, it's 70 centimeters, which means measured from the 50 centimeter mark, this will only be 20 centimeters. And I get about 0.45 Newton meters when I multiply that out. Now, I'm going to run into the holes in my paper here, so let's do counterclockwise over here. The only thing causing counterclockwise is this weight, 1.12 newtons, and it's at 10 centimeters from the 0, which means it's at 40 centimeters from the 50 centimeter mark. 0.4 meters. And if I multiply those out, I get 0.45 Newton meters. Now, since these two torques are equal, remember that means this thing has no angular acceleration, so it's not going to suddenly start spinning on us. For my final part, I'm going to need a little extra paper. So let's do this. I am now going to consider rotation at the 100 centimeter mark over here. Now, my intuition tells me this problem is symmetric between these two pivot points. So I imagine I'm going to get the same answers as when I did it over here, but let's check that out. So for my clockwise torque, if I'm measuring from the 100 centimeter mark, I have only the upward force making this thing spin clockwise. Think about it. All these downward forces, if we're considering the rotation here, will make it spin this way, which would be counterclockwise. So for my clockwise torque, 3.86 newtons, 0.5 meters, 1.9 Newton meters. Now from the previous problems, we already know this thing is not spinning, and so we can conclude its net torque is 0. It could also just have constant angular velocity, which we'll get to in much later units, but not spinning or constant angular velocity. So I can go ahead and conclude that the torque counterclockwise is also 1.9 newtons, just because reality is consistent, and I got answers in the other problems telling me it's in equilibrium. But why don't you check it to see if you can do it on your own? Go ahead and find the torques from each of these three weights and see if they sum to 1.9 Newton meters.